Chapter 5 still, Section 5.2, Atomic Spectra and Energy Levels. After this video, make sure you go and look at the video problems for 14 and 15. So, atoms emit photons when they are heated. So you're going to be doing a lab about this, and you'll take some chemicals. All right, so let's just say here's the chemical, and you're going to put energy into that chemical via a Bunsen burner. And you'll see that this gives off visible light when it's heated, when energy is put into it. And so what it's really doing is it's giving off a photon. Now a photon is a packet of light. And that packet of light is a defined amount of energy. And this was a big idea, real big idea. We'll talk more about it in AP. So there's a general term, quantum. Quantum is a packet of energy. So it could be any form of energy. A photon is a packet of light energy. Okay, so there's a little bit of a difference. But what they found was that when they do this, when they excite this compound and it gives off light, and they pass that light through a prism, they find that that light is broken up into representative wavelengths. So we get what's called an atomic spectrum. So like here's a couple of atomic spectrums. Here's strontium. So when they heat strontium up, and strontium is one of the chemicals that you will use in the lab, and they spread that through they make that spread out through a prism, they'll get these very distinct waves here, very distinct colors. But strontium always gives that off. And guess what? Nothing else gives that off. Same thing with here with barium. It's more of a green light here, but still the same thing. You know, it's broken up into these wavelengths. And so why is it? Why is it that atoms, when they are excited, they only give off certain wavelengths of light? Well, the reason why they only give off certain wavelengths of light is because of energy levels. Right? So what we have right now is sort of this Bohr idea of an atom. So here's the nucleus, here's the first energy level, here's the second energy level, here's the third energy level. That's sort of what we have right now. And so what happens is that here's an electron on this energy level. Right? We put energy into the system, and we'll talk more about this actually in the coming up too. So we put energy into the system. This electron jumps up to a higher energy level. But it's not stable up there, so it immediately comes back down. Well, this was energy. Let's say that that's 15 kilojoules of energy. Let's say that this is 5 kilojoules of energy. So in order, negative 15, negative 5, sorry. In order to jump up, it had to gain 10 kilojoules of energy. Well, in order to jump back down, it has to give off 10 kilojoules of energy. And that 10 kilojoules of energy is a certain wavelength of light. So I want to talk specifically about this idea a little bit here, okay? Because I want to make sure you know it's not the electrons that determine the energy, it's the energy level itself. So the example I want to give is I want to give you the potassium ion and the calcium ion. Right? Now, both of these have the same number of electrons. Okay? So a calcium 2+ ion has 18 electrons. A potassium +1 ion also has 18 electrons. But they give off different wavelengths of light. So same number of electrons, different wavelengths of light. So what is it that determines that wavelength of light? Well, potassium has 19 protons, calcium has 20 protons. So what happens is these 19 protons exert a certain force of attraction for these electrons. And that's not odd to you guys. We know that opposites attract. And we also know that we can measure that force of attraction. Well, here is, will 20 protons have the same, less, or more force of attraction for the same number of electrons? Yeah, 20 protons will have greater force of attraction. So what happens is that these electrons in this calcium 2 plus ion, they're actually closer to the nucleus. They're pulled in closer because these protons are pulling with stronger force, more force than these protons because there's more of them. 20 is greater than 19. Go ahead and use your calculator, check it out. 20 is greater than 19. So it is the energy level that determines the wavelength of light that's given off, not the electrons themselves. And we can talk more about this during the lab if you'd like, or post some questions on the discussion board. All right? So what they came up with, this idea is that these energy levels, they're all quantized. And to be quantized means that they have a defined amount of energy. Okay? The energy is not spaced equally, and so basically, the higher up in energy you go, the closer the energy levels get. So they often say, think of it like a ladder. So here's a ladder. Here's the first rung of the ladder. Right? Here's the second rung of the ladder. Here's the third rung of the ladder. Here's the fourth rung of the ladder. So they get closer and closer the further up you get. Okay, and that's what the energy levels do. They get closer and closer together. And that's important because the closer they are to each other, the easier it is for those electrons to move up and down. And that's what we do in fireworks. So the electrons can move between energy levels. But like I said, those energy levels are quantized. So let's go back to this idea up here. Okay, I'm going to draw that idea again down here. So basically what we say is the electron leaves at 0 energy, right? So this first energy level, we can say that that's something like negative, well here I'll stick with what I said, but I'll use joules instead, negative 15 joules. So the second energy level is 5 joules away, it's negative 10 joules. The next energy level is maybe only negative 8 joules, so now we're only 2 joules. Then maybe the next energy level, and I'm going to come down here, is maybe negative 7 joules, right? But to move between energy levels, so here's this electron that's on negative 15, in order for this guy to go all the way up to this top energy level right there, which is the negative 7 joules energy level, well, it has to gain 8 joules of energy. If it doesn't gain 8 joules of energy, it doesn't move up to that energy level. And it can't gain 7.5. Like it can't get right here at all. It can't exist between energy levels. Either it's on the energy level or it doesn't go at all. So let's say that we do. So let me draw this again. So there's 8 joules. So let me draw some arrows here. That's 8, 10, that's 15, that's 7. So let's say this electron does in fact gain. So it gains 7.5 joules of energy. All right. So what it's going to do is it's going to go up to this energy level, which is 8 joules, right? Negative 8 joules. So it's using 7 joules of energy, and then a half joule of energy is just given off. It's not used, right? So that's to move up energy levels. It has to absorb energy to move up energy levels, because those energy levels, the further away they are, those energy levels have higher energy. They have greater energy, right? Negative 8 is bigger than negative 15, right? As soon as they get up there, though, so as soon as they jump up to that higher energy level, they're going to come right back down, and they're going to lose energy. And when they lose energy, well, guess what? The difference between the energy levels, in this case, 7 joules, so that's 7 joules between those energy levels, that's how much it has to give off. So it would have to give off 7 joules worth of energy, because that's the difference between the energy levels. Sorry, that was my phone. I apologize. Now, when it gives off that energy, it can be in all sorts of wavelengths of light. So, we go back up here to look at the electromagnetic spectrum. That's how it gives off the energy. It's somewhere in this electromagnetic spectrum. So maybe it gives off, like in the lab that you're going to do, it gives off visible light. So there's a very small region of visible light. Maybe this morning you used a microwave. Maybe you got an X-ray at some point. But all of this is because of electrons absorbing energy, moving up energy levels, then electrons releasing energy coming down. And when it releases that energy, that's when it releases somewhere in this electromagnetic radiation, the electromagnetic spectrum. Okay. So again, here's the electron living on some energy level. Let me use a different color. Black's not going to be efficient there. All right? We put energy into that system. The electron jumps up. Okay? Now, how much energy is this? Well, it depends on the difference in the energy levels. If the difference in the energy level is 30 joules, then we need to put 30 joules in there. If the difference in the energy level is 1 times 10 to the negative 18th joules, well, then that's how much energy we need to put in here. If we wanted to jump up even higher, we have to put even more energy into it. And then at a certain point, we put so much energy into it that, boom, the electron leaves the atom. And we'll talk about that specifically.